So in exercise 20.42, we're still doing multi-step synthesis with aldehydes and ketones. But the question is being presented in a slightly different way. And if you like puzzles, then this will be a fun sort of exercise. Probably on the test, there are two questions on multi-step synthesis for aldehydes and ketones. Probably one of them will be like 20.41, and another one will be like this one, 20.42. Okay. It says, using any compounds of your choosing, so that's exciting. We have all of the handbook of Sigma Aldrich or Fisher Scientific at our fingertips. Identify a method for making each of the following compounds. Your only limitation is that the compounds you use can have no more than 2 carbon atoms. So we can't use any carbon chain that's larger than 2 carbons. We can use stuff that has functional groups on it. We just can't use anything that has more than 2 carbons. It says, for purposes of counting carbons, you may ignore the phenyl groups of a Wittig reagent. Remember that in Wittig reagents you have a phosphorus double bonded to some carbon. It doesn't have to be a carbon with 2 hydrogens on it. It could have, for example, an R group on it. What they're talking about, though, are the phenyl groups. So you remember the phosphorus has those 3 phenyl branches. Those are, each one of those is a benzene ring acting as a branch. So that's what the capital P lowercase h is meaning. And there are 6 carbons in a benzene ring. Well, our limitation is that we can only use 2 carbons. So what they're saying here is you may ignore the phenyl groups of a Wittig reagent. So you can use Wittig reagents. These don't count as part of the 2 carbon limitation that they're shackling us with. We only have to worry about the carbons, because these really don't get added to the carbon chain that we're changing. We're just worrying about how we make that carbon chain. Okay. Now, this is kind of fun. It's an especially fun exercise because it's easy to get a 2 carbon chain. All you need is ripe fruit. There's the simplest alkene you can have, ethene, so like you have carbons here and then hydrogens on each side. That is a plant hormone. That is the hormone responsible for making all fruit ripen. Across species, that makes all fruit ripen. So much so that if you have a ripe fruit, let's say you have like a spherical apple here, and you have a ripe fruit, that's your apple, that is emitting gas all the time. It's producing this ethene gas, that's what makes it ripen, and then that gets secreted out into the room. That's the reason why if you take something like a ripe apple and you put it in a bag with, say, an unripe avocado, the gas, the ethene gas, ends up going into the avocado and ripening the avocado. So you can ripen fruit just by putting a fruit that is already ripened, so secreting this ethene gas in a closed container with an unripened fruit. The gas will go into the unripened fruit and ripen it. So it's easy to get this ethene gas. All you have to do is take a ripe fruit, and you can put it in an Erlenmeyer flask. So remember, those are those flasks that sort of, here, let me move this around. Those are those flasks that sort of are V-shaped. They have the little nozzle there. And then what you can do is put a cap on it, but make sure the cap has a hole right in the middle. Connect the hole, and so you have like a cork that you put in here, but the cork has that hole. Then you use a piece of glassware, and this is a useful trick in general to capture any gas. You use the cork, you put a little piece of glassware, an arm of glassware, and they have these in lots of different shapes, and you can connect one shape with another. And what you want to do is submerge this arm underneath water. So actually, let me... So take a piece of like a glass tube, and then just submerge that underneath water. So you can just have a regular old beaker, and you can have a test tube that you want to put upside down. So you want to orient this so that it's facing an upside-down test tube. Meanwhile, we have water. So what ends up happening is as the gas gets secreted, it tries to leave the container, and when it does, it travels through this tube, goes underneath the water. It's not connected to the water yet, it's protected from the water, and it bubbles out into this upside-down test tube. And so you collect the gas in this upside-down test tube. So you can collect ethene gas that way, and once you have ethene, you can make any of these two carbon chains that we're talking about. And you could do all the tricks that we've learned in previous sections. For example, you could do addition of H and OH. You could do acid catalyzed hydration, water and sulfuric acid, and that would turn that into ethanol, drinking alcohol. And you could do addition of hydrohalogenation, right? H and Cl, stomach acid, mix it with stomach acid, and you'll end up with a chlorine there. And then you can do substitution reactions or what have you. So it's sort of a really fun application. All these two carbon chains that we are going to deal with, you could get basically from the gases secreted by ripe fruit. So that's why this is a particularly fun exercise. Okay, so we cannot use any carbon chain larger than two carbons. Otherwise, we can use anything to make this. We're limited only by our creativity. Well, as you've seen sometimes, having too many options can be frustrating. It's more satisfying only having a few, because then you know you're on the right path, right? You don't feel like you've made any bad choices, or you don't feel daunted by the possibilities. So let's deal with this limitation and use this as a strength. If that's our limitation, that tells us, that narrows down what our synthesis has to be. Well, we have 1, 2 carbons here. So imagine cutting that chain off, and then 1, 2, getting another chain that's 2 carbons long. We can't start with any chain that's longer than 2 carbons. So let's imagine those two pieces. We have this one on the left, and we have this one on the right. So that's like that there. Now let's think about what we can do with each of these. What we want to do is form a new carbon-to-carbon bond, and the carbon-to-carbon bond is going to be a sigma bond, a single bond between these two carbons, the carbon here and here. We want to make a sigma bond between those, and that's a sign that we need to use a Grignard reagent. There are lots of ways to make carbon-to-carbon bonds, but the way that what you can do to make a carbon-to-carbon single bond is a Grignard. Now, this molecule has a whole bunch of stuff on it. That means we have more options with it. The molecule on the right doesn't have anything on it except for carbon and hydrogen, so that's a good option for our Grignard reagent, because there's nothing that could be electrophilic there, but we do have a carbon that can be nucleophilic, aka the Grignard. So if we imagine having sort of a bromine here, and then if you mix that with solid magnesium, you'll get your Grignard. Just make sure there's no water in that solution, otherwise the Grignard reagent, once it forms, will react with the water. So usually the solvent people use is diethyl ether, which, remember, would look like that. And you have your Grignard reagent. Okay, so that's one thing. But the Grignard reagent, this is a nucleophile, and it needs an electrophile to attack. So how can we get an electrophile out of this molecule on the left? Well, what we see that we have here is an imine. We have a nitrogen double bonded to a carbon. It's the nitrogen version of a carbonyl. And you can make imines by combining a nitrogen that has at least 2 hydrogens on it. Those 2 hydrogens are going to get replaced by the double bond. And the third thing is whatever the third thing is on the nitrogen. So in this case, it's a hydrogen. We can make that amine by combining ammonia with this aldehyde, which happens to be called acetaldehyde. It's a common name worth knowing. That's acetaldehyde, a common name worth knowing because sometimes it'll appear on standardized tests. They'll expect you to know what that is. I won't expect you to know what that is necessarily on this test. So So if we have these two things, we could definitely make this imine. And how can we get this, though? Well, actually, technically, we could just start with that, right? We could start with that because we can make anything. We can use any reagent. Our only limitation is the number of carbons. But if we did this, we'd still be missing the other two carbons in the molecule. So what we'll need to do first is to connect the two carbon branches. And after we connect them, we can form this imine. Now notice, we have an aldehyde here. That means that we have a great electrophile. This carbonyl carbon is slightly positive because it's losing its electrons to the slightly negative oxygen, and so this Grignard reagent will totally attack that carbonyl carbon and kick the electrons up. Okay, so that's how we can get the right carbon chain. If we take acetaldehyde and react it with ethyl magnesium bromide, that ends up giving us the 4 carbons. The oxygen now just has a negative charge. Right, if you follow this, we have 1, 2, 3, 4, 1, 2, 3, 4. The carbonyl carbon, the double bond to the oxygen, turns into a single bond, and the pi electrons go onto the oxygen and give it a negative charge. So that's our first step. Now, to stabilize that negative charge, we just treat it with some water. This can steal one of the hydrogens from the water, as we've seen before, and that would form this. So we're kind of close. Ultimately, we just want to turn this into an imine. Well, for an imine, you just need the amine, primary amine, and a ketone, or an aldehyde. So our next step with this carbon chain is to turn this into some sort of a ketone or an aldehyde. Now we only have 1 bond to an oxygen here, we have 2 in the product, that's an oxidation. This alcohol, the carbon that has the OH on it, is bonded to 2 other carbons, so it is a secondary alcohol, which means you can use a strong oxidizing agent like sodium dichromate in water and acid. If it were a primary alcohol, if the carbon that had the OH on it was only bonded to 1 other carbon, if you wanted to form an aldehyde, you'd use PCC, pyridinium chlorochromate, as we've discussed in a previous video. But here we have a secondary alcohol, and so we can use a strong oxidizing agent like sodium dichromate to turn it into a ketone. Well, we're almost done. All we need to do is turn that oxygen into a nitrogen with a hydrogen. And that is imine formation. So we need to have a nitrogen with 2 hydrogens on it. Those 2 hydrogens are going to get replaced by the double bond to the carbonyl carbon. And the other thing, the third bond to the nitrogen, will just be whatever we need, whatever is drawn in this product. And that's a hydrogen. So we need yet another hydrogen. And when you do that reaction, you end up getting your imine, which is the molecule you wanted. So as you're thinking through these, the first step is to chop the carbon backbone into 2 carbon branches. And then think about what you can do with each of those branches. If something only has a carbon on it, use it as a Grignard reagent. Start with a bromine on it, and then just mix that with solid magnesium. That gives you your Grignard. That's your nucleophile. The other thing needs to be an electrophile. Remember that you can form imines by using an amine that has at least 2 hydrogens and an aldehyde or a ketone. You can also use an aldehyde or a ketone as the electrophile for Grignard reagents to attack. So you can attack those. Once you do the Grignard reagent, treat it with water to stabilize the negative charge, oxidize it to get your ketone back, and then treat it with a primary amine, or at least an amine that has 2 hydrogens, and that gives you your imine. So the steps that you would want to write here is first the ethyl magnesium bromide, you could have this as your answer. First, ethyl magnesium bromide. It gives you this. Stabilize the negative charge with water. It gives you this. Oxidize that alcohol, the secondary alcohol, with sodium dichromate in water and sulfuric acid. And then turn the ketone into an imine by adding an amine that has at least 2 hydrogens. The third group will be whatever you want left on the nitrogen after it forms the imine. And that will give you that product. Okay. Pretty fun, pretty fun. Then if we look at B, same idea. We need to form this, but we can't use anything more than 2 carbons at a time. So let's divide the carbon backbone here into 2 carbon lengths. So 2 carbons and then a break. 2 carbons and then a break, right? So 1, 2, break, 1, 2, break, 1. Now let me write those 3 pieces separately. I'll have that one on the left, and then our break. The one in the middle, and then the break, and just a single carbon on the end. So I'm actually going to write that as a CH3. So those are our pieces, if we're in terms of, we're thinking of the longest carbon chains we can use. Now, this one at the very end has nothing on it. All it has is carbon and hydrogen. And so the only thing we can use that for is a Grignard reagent. Notice again, just like in the one we just did, we need to, every place where we broke, that's a carbon-to-carbon single bond, carbon-to-carbon sigma bond, that needs to be formed. And so we can recreate that, we can reattach that, reattach the 2 fragments on either side, this one and this one, by using a Grignard reagent. So since all this has is carbons and hydrogens, we can use that to make the Grignard reagent. So we'll just have a bromine on it. If you needed to put a bromine on it just from the alkane, then you can do that with NBS and heat. Right? The only thing that will react with an alkane is a radical. But once you have that, you can dunk some magnesium in with that, and that turns into the Grignard reagent. So that's that piece. This piece will clearly be our electrophile. That's the part that has the weird stuff on it. We'll come back to that in just a second. Here again, you can see that there's only carbon and hydrogen there. So again, to reattach where we broke, to recreate that sigma bond between the 2 carbons, we need to turn this into a Grignard. So imagine methyl bromide, dunk some solid magnesium in that, and that would give you methyl magnesium bromide. So we have those 2 Grignard reagents. Okay, well, how about next? When we look at this thing in the middle, what you would hopefully recognize that as is an enamine. You have a double bond, hence the ene. You have a nitrogen with all single bonds around it, hence the amine. So it's an enamine, and you form enamines when you mix an aldehyde or a ketone with a secondary amine. And when you're trying to think about what amine you need to use, draw the nitrogen with its 3 bonds. The 2 bonds that are not going to the carbon chain, those stay. These 2 carbon bonds at the top. The carbon bond that is going toward the double bond, toward the carbon chain, that gets turned into a hydrogen. So that's going to be the amine we want. And notice that that is a secondary amine. This nitrogen is bonded to 2 carbons. So you get a secondary amine, and you mix that with an aldehyde or a ketone. Now, the aldehyde or the ketone is going to be going toward the bond where the nitrogen is. We drew the mechanism for how this forms in a previous video, so I won't belabor how that works here. But remember, those are the puzzle pieces that you need. You need an aldehyde or a ketone. The double bond to the oxygen is going in the direction of the nitrogen. And then you need a secondary amine. And if you mix these two things together, you'll get your enamine. Okay, well, these are our pieces so far. Now, in this case, we do have a good electrophile on that carbon. The carbonyl carbon is slightly positive, the oxygen is slightly negative. And so we could react that with, say, this nucleophile and add that carbon chain there. You always want to try to create the carbon chain first before you start doing these other reactions, like the creation of the enamine or the creation of the imine, like we saw in the last one. So let's try to connect all of these. The trouble is we need a carbon nucleophile to attack at both of these positions. We need this nucleophile here to attack on the right, and this nucleophile here to attack on the left, right? Because this here is sandwiched in between those groups. Well, we already have a good electrophile there on the left, but we need a good electrophile on the right. Now, it might take a little bit of an imagination to see this, but we have an oxygen. How can you make with just one oxygen, how could you make this two-carbon chain have two electrophiles? You have a two-carbon chain and one oxygen. How could you make both of the carbons electrophilic? And the answer is by connecting both of the carbons to the oxygen so that you get oxirane, that smallest of epoxides. And remember, these epoxides, normally ethers, oxygens that have single bonds on both sides, normally those are not single bonds to carbons on both sides. Normally those are not especially reactive. But because of the ring strain, you're forcing these sp3 hybridized carbons, which would prefer to be 109.5 degrees, have 109.5 degrees between all their bonds. You're forcing those to have 60 degrees between their bonds. And that means that this wants to really pop open. That, combined with the slight positive charge on these carbons, because they're losing electron density to the electronegative oxygen, makes that really reactive. So, for example, the one we were worrying about was this carbon on the right. But if we take methyl magnesium bromide and react it with this epoxide, so remember this is really like an ionic bond. So you'd have the magnesium there with almost a full positive charge and the carbon with almost a full negative charge. Actually, it's a little bit more covalent than that, but it's really, really close. So the carbon can act as a nucleophile, attack one of the carbons in the oxirane, kick the electrons onto the oxygen so that the ring bursts open in a flash. And then we have this molecule here. So let's number these so we can follow. 1, 2, 1, 2. Notice the oxygen stays on carbon number 1. And this is carbon number 3. Okay, so that is our new structure. Now, anytime you use those Grignard reagents, it's always good practice to stabilize the positive charge using water. Or you could use a mild acid, but water's usually fine, so you can have that. So we have 1-propanol, or yeah, 1-propanol now. Well, it's not so bad. We've connected these two carbon chains, but we still have to connect this other carbon chain with this other Grignard reagent. So we want to add a Grignard reagent, but before we do, we need a good electrophile here. That's where we want to connect it. Not so bad. We know we can create good electrophiles by creating carbonyls. Now this is a primary alcohol. The carbon that has that OH on it is bonded to just one other carbon. And when you oxidize primary alcohols to aldehydes, like this is, right, there's an implied hydrogen there because only 3 other bonds are explicitly drawn in. So this is an aldehyde. When you oxidize primary alcohols to aldehydes, you have to use the weak oxidizing agent pyridinium chlorochromate, or PCC. If you used a strong oxidizing agent like sodium dichromate and water and sulfuric acid, it would take that to a carboxylic acid, which has a completely different reactivity that we'll learn about in the next chapter. Well, once you do that oxidation, this is now a good electrophile. It's losing electron density to the oxygen, and it has a good leaving group in the form of the pi bond, so you can attack it with a strong nucleophile like the Grignard reagent. This carbon will attack that there, pi bond breaks, goes onto the oxygen, and so we end up, and let me number these so we can follow these a little bit more easily, 3, 4, 5. So we're going to end up with a 5-carbon chain. 1, 2, 3, 4, 5. So let me number these again. 1, 2, here's our new bond that we formed. 3, 4, and 5. Now carbon number 3 is still going to have that oxygen on it, it just won't have 2 bonds. The pi electrons would have gone onto that oxygen and given it a full negative charge. So you can stay, anytime you do those, use those Grignard reagents, follow it up with water to stabilize the charge, negative charge. So now we have this. Okay, and we're pretty close. If we go back up here, we're looking for what we're trying to make. It's this here. What we've created by this point is this molecule. Now that we see them side by side, hopefully it makes sense that all we have to do is add the secondary amine, and it turns this ketone into an enamine. So we can take our secondary amine, and actually, first we need to turn this into a carbonyl, but that's relatively straightforward. If you want that to be a carbonyl so that you can form the enamine, you just have to do an oxidation. There's only 1 bond to oxygen here, there's 2 in what we want. So in oxidation, the carbon that has the OH on it is bonded to 2 other carbons, so it is secondary. You can oxidize secondary alcohols using sodium dichromate, water, and acid. So that turns that secondary alcohol into a ketone. Once you have the ketone, you can react it with that secondary amine that we talked about earlier that replaces the 1 bond to the hydrogen with a bond to the carbonyl carbon. And there's a proton transfer step at the end of that mechanism that you have to do from the beta carbon and the carbon next to the carbonyl for where the nitrogen is attached, and that gives you your enamine. All right, so overall, let's review what we did. We started, first I'll review it, then I'll write all the steps down together. When we were looking at the molecule, we broke it apart into 2 carbon chunks. 2 carbons, 2 carbons, 1 carbon. Because we can't use anything more than 2 carbons. That's the rule for this. That's the restriction they're giving us in this problem. Anything that only had carbons on it, we turned into a Grignard. What had the functional group on it was what we knew would have to have the oxygen on it. We noticed that the functional group was an enamine, and so we formed those with a secondary amine and an aldehyde or a ketone, where the carbonyl is going toward the nitrogen. Then we realized that we needed good electrophile on both of the carbons in that aldehyde in order to attach it to the two Grignard reagents. We needed Grignard reagents to attach on both sides, so we needed both of those carbons to be electrophiles. And the only way we found to do that, or the quickest way we found to do that, was to take the oxygen and bond it to both of the two carbons. That's a reactive epoxide, oxirane. We can treat it with one of our Grignard reagents, and that opens the ring up. Treat it with water to stabilize the negative charge. Oxidize that with PCC so that we have a good electrophile, and then we can treat it with the second Grignard reagent. Stabilize the negative charge with water. Oxidize it so you have the ketone, and now you can just treat it with your secondary amine to get your enamine. So all together, we had an oxirane ring, and the first step was treating that with methyl magnesium bromide. Remember, the Me is a CH3, it's a methyl group, followed by water to stabilize the positive charge, the negative charge on the oxygen. And then we oxidized that with PCC to the aldehyde. Right? Once we had the aldehyde, we could treat it with our other Grignard reagent, in this case ethyl magnesium bromide. Treat it with water to stabilize the negative oxygen. Oxidize it with your oxidize that secondary alcohol that we made with your strong oxidizing agent, sodium dichromate, in water and sulfuric acid. And finish the whole thing off with the secondary amine that you need. Now, if you really wanted to do a good job in that last step, you would want to treat that with some sort of catalytic acid, if you remember the mechanism. And if you dehydrate it, if you heat it up so water is evaporating at the end, that'll push the equilibrium even further to the right and increase your yield. So those two details would help with that. And so you'd have a sort of 7-step synthesis for this. So pretty exciting. All right, let's try one more in this video. Let's try making C. Now again, the first step is going to be breaking this up into 2 carbon branches. So break it up. So we have 1 carbons, 2 carbons, break. 1 carbon, 2 carbons, break. 1 carbon, 2 carbons, okay. So we're going to have 3 different pieces. We'll have this piece on the left, then we have the break, and we have the piece in the middle, and then we have the break, and then we have the piece on the right. Now notice the only thing that has more than carbon and hydrogen is this piece on the left. That has this acetal carbon with an ether on both sides. Well, if something only has carbons on it, we know that eventually both of these are going to have to act as Grignards. The tricky thing is that we need to form a bond between these two. Now this one has to, one of these absolutely has to act as a Grignard reagent. So if, for example, we have ethyl bromide and you dunk that in some magnesium, then you have ethyl magnesium bromide. So that's a good Grignard reagent there. Some solid magnesium you'd put into that ethyl magnesium bromide, 1-bromoethane. Now you need this to attack this other carbon, which means that we have to somehow make this, we have to make that an electrophile, because this here is our nucleophile, carbon with a negative charge. So we need to have an electrophile here, somehow. So we have to think about how to do that. At the same time, on this other position, we will ultimately need a bromine. Just like here. Mix the bromine with the magnesium so that that can become a Grignard reagent and attach to this over here on the left. Okay. Well, it may not be clear immediately how to get the bromine, but if we do a similar trick as before with the epoxide, then this carbon will be slightly positive. Both of them will be. It doesn't matter. It's a symmetrical molecule. And we may not get a bromine, but at least we'll have something where we need the bromine. Maybe we'll be able to do a magic trick and turn the oxygen into a bromine somehow. We'll think about that when we get there. So if we have this epoxide, oxirane, which is slightly positive, carbons on both sides, because the oxygen is stealing electron density from them. And I'm going to draw this ethyl magnesium bromide as two separate things. Oops. It's almost an ionic bond. It's something like that. The carbon anion there can attack one of these carbons, burst open the ring, and you end up getting a 4-carbon ring now, because you have 1, 2, 3, 4. So 1, 2, 3, 4. So you form this new bond between carbon 2 and 3. The oxygen had 2 lone pairs. Now it has 3, because it got the electrons in this bond. That gives it a full negative charge. Anytime you do those Grignard reagents, it's good practice to follow it up with some water just to help stabilize it so it doesn't break down or react with anything else. So we'll have 1, 2, 3, 4 carbons, and then now an OH after the water. Okay, well, that's not quite what we wanted. We wanted that, but with a bromine there. But maybe there's a way, because really we want this to be a Grignard reagent somehow, so that we can attach it to this other last fragment. But there is a way to turn an alcohol into a bromine. And you would have learned it in the alcohol chapter. We haven't seen it much after that this semester. But in the alcohol chapter, you would treat that with phosphorus tribromide. And that turns an alcohol, the OH, into a bromine. Now that probably looks like black magic, so let's talk about how that happens. It really happens through 2 successive SN2 reactions. This is a bad leaving group. You want it to leave, and you want it to get replaced by a nucleophilic bromine. Well, this phosphorus tribromide provides the nucleophilic bromine and turns this into a good leaving group at the same time. Let me draw it going the other way. Let's say we have this. This oxygen is kind of nucleophilic because it has those lone pairs and a slight negative charge. Phosphorus tribromide, the bromines are more electronegative than the phosphorus. So they pull electron density to themselves. The phosphorus becomes slightly positive. The bromines are slightly negative. And the oxygen attacks the slightly positive phosphorus and kicks one of the bromines off. You end up with this weird looking thing. The phosphorus only has 2 bromines now. The oxygen here has a full positive charge, and this is an amazing leaving group. Because if this oxygen accepts the 2 electrons in that bond, it can do that. It'll help stabilize the positive charge, and it'll be a stable molecule. The bromine that you ended up kicking off comes back as a nucleophile and attacks that carbon, kicks the leaving group off, and you end up with the 4-carbon chain, but where the OH was, you have a bromine. And you also end up with this side product, this phosphorus with 2 bromines on it and an OH. But the important thing is the carbon chain. So long story short, that's a simple mechanism. It's just 2 successive SN2 reactions. This is an SN2 reaction. This is an SN2 reaction, nucleophilic attack and loss of a leaving group happening at the same time. Long story short, though, is that this phosphorus tribromide replaces an OH with a Br. So we can treat it with that phosphorus tribromide. Now we have a bromine on it, and we could dunk some solid magnesium in there. That'll turn that into a Grignard reagent, which is now a nucleophile that we can use to attack this last piece. So let's talk about that last piece. You have an acetal, and anytime you see an acetal, especially after learning the mechanism for it, you should see an equilibrium between the acetal and a carbonyl. So really, we want this carbonyl. That carbonyl is a good thing to react with our Grignard because it has an awesome electrophile. It has a slightly positive charge on the carbon and a slightly negative charge on the oxygen. This carbon here, which has a really it's an ionic bond. We can redraw that. It's almost like this. The nucleophilic carbon can attack the carbonyl. The pi bond breaks, goes onto the oxygen, and that gives us, and here just to keep track, let's number this. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. On carbon number 2, we will have just one bond to an oxygen. The oxygen will have a full negative charge. And that's it. Anytime you use a Grignard reagent, it's always good practice to add some water to help afterwards to help stabilize the negative charge in the oxygen. I emphasize the afterwards because if a Grignard reagent is mixed with water itself, it will react with the water before it does with the carbon chain. The negative carbon will just steal hydrogen from water instead of reacting with your electrophile. So you never want to mix the Grignard reagent with water. You want to follow the Grignard reaction by a separate step of a water wash. All right, well, we're almost there. We have our 6-carbon chain, so at least we've got that. Now we just need a carbonyl here, and then we can use a diol to create the acetal. So let me make a little bit more space. Okay, let me draw the structure we want below this, just so we can compare. That's what we want. That's what they assigned us to create. So what do we need to do? Well, when you see this, you should see an acetal, carbon with an ether on both sides. And so you need two things. You need, to make an acetal, you need a carbonyl, and you need a diol. Now here, the diol is, the two alcohols are going to be connected. There's a 2-carbon chain with alcohols on both sides. To turn them into an alcohol, you just need the H's. So those are your two pieces. And you'll get your product. In order to get this ketone from the alcohol we have, all you have to do is an oxidation. This has 1 bond to an oxygen, this has 2, so it's an oxidation. The carbon with the alcohol on it is bonded to 2 other carbons, so it's secondary. That means that you can use a strong oxidizing agent like sodium dichromate in water and sulfuric acid. That'll turn the secondary alcohol into a ketone. Once you have that, treat it with your acetal. Remember that you need some catalytic, oops, let me just erase this one. Remember that you need some catalytic acid to make that happen in the mechanism. So include that there. And if you heat the product up so that water starts evaporating, so you remove the water, that uses Le Chatelier's principle to shift the equilibrium in the direction of the acetal. So that'll increase the efficiency of that reaction. And that would give you your acetal, combining your ketone with your diol. All right, let's review what we did, and then we'll write all the steps down just over one arrow, which is technically the answer, because in these questions on the exam, you don't have to write the mechanisms for all these. I'm writing them so that you can see the reasoning behind it and why the series of reactions makes sense. But you don't have to provide those necessarily on the test, so long as your synthesis is correct. So what we did is we took our carbon chain and we cut it up into the largest pieces we could, 2 carbon pieces. That was the rule they gave us in the instructions to the problem. So we thought about each of those pieces separately, 1, 2, 3. The pieces that only had carbons and hydrogens on them we knew had to be Grignards. So we made a Grignard out of the one on the end, but to attach it to the one in the middle, we had to create some sort of an electrophile. So we did an epoxide. The epoxide opened from the Grignard reagent. We used water to help stabilize the negative charge, and that gave us an alcohol. Now that's kind of convenient. It's kind of convenient because we have something there to work with. We just have to turn that into a bromine in order to make this another Grignard reagent, and we did that with phosphorus tribromide. Phosphorus tribromide replaces an OH with a Br. Drizzle some solid magnesium into that mixture, turns that into a Grignard reagent, which you then can react with acetaldehyde. Grignard reagent attacks the carbonyl carbon, stabilize the negative charge with water, and you have 2-hexanol. Now that's pretty close to what we want. We made the carbon chain. We just have to create the acetal. To get an acetal, you needed a ketone, so we had to oxidize our alcohol. It's a secondary alcohol, so we use a strong oxidizing agent like sodium dichromate. Once you have your ketone, you can treat it with a diol. Remember to include some catalytic acid and preferably remove some water at the end to shift Le Chatelier's principle toward the products, and that gives you your acetal. So overall, what we did is we started with that epoxide. Let me actually move this down here. So we were trying to make this acetal. So we started with our epoxide. The first thing we did was to react it with methyl magnesium bromide, or ethyl magnesium bromide. That gave us our 4-carbon chain. We treated it with water to stabilize the oxygen. We replaced the OH, alcohol, with a bromine by adding PBr3. Then we mixed that with solid magnesium to make the Grignard reagent. We reacted that with acetaldehyde to attach that 4-carbon chain to the other 2 carbons. After that Grignard reaction, we treated it with water to stabilize the negative oxygen. We oxidized that secondary alcohol using sodium dichromate in water and sulfuric acid. And then we reacted that ketone with our diol, the appropriate diol, to make the acetal, being careful to provide some catalytic acid and hopefully removing, that's a minus sign, some water from the products. Removing the products shifts equilibrium to the right through Le Chatelier's principle. So there's sort of 8 steps here that we needed to do in order to create that piece, that work of art, that acetal from just 2 carbon chains. So we'll continue this exercise in another video. I don't want to make these videos too long. But this is just another multi-step synthesis problem, just framed in a different way.